Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program. Local broadcast is made possible in part by Pfizer.
As an astrophysicist, special relativity is a natural theme for me to cover. Special relativity can be summed up as big consequences of an observed phenomenon. Everyone observes the same speed of light, and nothing in the universe can go faster than the speed of light, which is the universe's speed limit. Special relativity is quite important in astronomy because there's a lot of energy out there in the cosmos, and many things have really fast speeds out there. Astronomy is the only place where we see large organized flows of material moving near the speed of light. There are a lot of weird special relativistic results, which only seem strange because we don't spend our lives moving near light speed. We have to get over our common sense to really understand what's going on at the speed of light. Today I will explain where some of these basic results come from. Next week, I will talk about the games that relativity plays with light and give examples of odd things we see in the universe, with examples from the high-energy universe like massive jets barreling off of galaxies. And for the third week, I'll talk about the universe's brightest explosions, gamma-ray bursts, and where relativity enters into these. I'll start by discussing what we mean by relativity in physics. And then how we understood this concept before Einstein came along. And then how Einstein formulated special relativity, which was adding to this physics concept of relativity a constant speed of light. And how this constant speed of light makes us disagree about such basic things as how fast we're aging, how long something is, or whether two things happen at once. So the principle of relativity can be pretty simply stated. It says that the physical results, so the results of an experiment, for instance, are going to be the same for two different points of view, which physicists call frames of reference, that move smoothly relative to each other. This means that it has something to do with your hot cup of coffee. You could imagine an experiment simply to be, you take your cup of coffee, and you put it down on the table in front of you. The result of the experiment is that the cup of coffee stays there until you move it or knock it over with your hand. Now, why is it that you can still do this in an airplane that is moving at tens of thousands of feet over the ground at hundreds of miles an hour? That's simply because the speed of the airplane is smooth relative to our speed at the ground. By the principle of relativity, we should get the same result from the two experiments. Of course, if there's an acceleration like turbulence, all bets are off. As another example, we're going to imagine tossing a ball up and down. What we have here is a cart and a ball. If you can see that, it's a little yellow ball, which will be visible against the dark background at the moment. We can put the ball into this cart, and the cart has a spring. The spring is set up with an optical eye over here, so that when it passes the eye, I'm just going to carefully put it here, it pops it up and it catches it. So your experiment is you're tossing a ball straight up and you see the ball come back down so you can catch it. Now imagine that you have 2 points of view. We have, I guess he's Super Duck over here attached to the cart. And he sees things from the point of view of the cart. We also have Godzilla's point of view over here. Now, as far as Godzilla is concerned, the cart, in a moment, is going to be moving smoothly along this track relative to him. I'm going to give it a little push. It's just going to keep moving on its own, so it's not going to be speeding up or slowing down. So if relativity is right, when the Super Duck ought to still be able to see that ball go up and get caught again. From his point of view. And Godzilla should also see the cart have the ball pop up and be caught again by the cart. So let's give this a try. Oops, that's not fast enough. There. There we go. What do you know? Physics is right. So we're going to quantify this slightly, and this is as scary as the math is going to get here, by the way. I don't ask you to remember any of these equations, but I want you to remember that they're simple. We have our 2 points of view called frames of reference. And to illustrate this a bit more carefully, I've got them also reproduced here. We're going to start out with a pink frame of reference. There are 3 directions going up to the back of the room and along the side of the room. You could also imagine that you have a clock ticking at the center of this. From the point of view of this frame of reference, these continue on forever. So any point here, the card over here, the computer, your seat, can be measured as a certain distance from the center of this frame of reference. Can I have a volunteer, please?
Okay, great.
I would like you to continue holding the pink frame of reference here.
There we go.
All right. I'm going to bring in a second frame of reference, the yellow frame of reference. Again, we have a direction up, to the back, and to the side. They could be put at the same place, at which point all points in the room, let's use Einstein as an example, will have a certain distance from them. We can also move one relative to the other. So I'm going to walk along with this one here at a smooth speed, and you can see what this does to our distance to Einstein. Just imagine I'm continuing to move. The direction up and down and towards the back hasn't changed, but the direction along this one is changing at a smooth rate from this speed. That's what we see in these equations over here. The position relative to this guy is changing with time relative to the position relative to that guy. That's enough now, thanks. You are released. This was known long before Einstein. They knew that this worked in terms of this relativity for motion. They're actually called Galilean transformations because it has a long pedigree going back to Galileo. And the simple result from this could be summed up with an example where you have boats moving on a lake. One point of view, one frame of reference can be the shore. Another frame of reference can be a boat moving directly away from the shore with a certain speed. They both see this other ship over here on the lake. That ship has a certain speed moving away from the shore. It also has a certain speed moving off this way. But the speed relative to the shore of this guy is going to be equal to its speed going away relative to the boat, plus the speed of that boat relative to the shore. This is natural. If this boat is moving away at 10 miles an hour, and this ship is also moving away at 10 miles an hour from this guy, you'd think that he has to be moving away at 20 miles an hour from the shore. It's the same thing as you see with cars on the interstate. If you're going at 70 miles an hour and another guy's passing you at 20 miles an hour, he's going at 90 miles an hour and could potentially be ticketed if there's someone out there. And for all you sports fans out here, another example of 2 different frames of reference is easy to see with basketball. If you have a player dribbling a ball across the court, there's 2 points of view. You've got the spectators in the stand that see the player moving, and you have the player's own point of view, the player's own reference frame. If the player has a reference frame with himself at the center, and all these distances are being pulled along with him, therefore, as far as the player's point of view is concerned, the player is still, and the rest of the court moves by him as he moves his legs. As he moves his legs, it makes the court go past him. And from the point of view of the player, the ball that he is dribbling is going up, down, well, down, up, down, up. He's just doing this. He doesn't have to keep on moving his hand around. It's just going up and down. From the point of view of a spectator, the player is also moving to the side. Therefore, when he sees the ball going up and down, what he sees is that, say, time 0, it's up here. After a certain time, the ball has gone down and forward with the player. And again, after another amount of time, the ball has come back up to the player's hand. But from the player's point of view, it's only gone down and then up. The spectator, if he was asked to say how far has the ball moved, this would definitely be longer than what the player would say the ball has moved. And therefore, because the spectator sees the ball go further in the same amount of time, the speed of the ball relative to the spectator is going to be faster than the speed of the ball relative to the player. Pretty simple and fairly common sense. As you can imagine, I'm going to have to turn it on its head later on in this talk. Our final example from the Galilean point of view involves a train. Physicists just love trains for explaining relativity. I'm not entirely sure why. I think it's possibly because this came during the steam age. But physicists have an ideal train. The physicist's ideal train is long enough that you can see delay effects between things being tossed at very high speeds across the train. It also has a completely glassed side with the windows. You can see exactly what's happening in the train. In my ideal train, there happens to be a guy at the front and a guy at the back. And they're both snoozing away. Well, someone has decided that we need to wake these people up. So we brought along a tuba. And this is a long enough train that you can see the difference between someone puffing on the tuba and when that puff, that sound has reached both ends and woken them up. If you take a look at it from the point of view outside the train, we have a station master on the station watching the train go by on the train tracks. And by some prearranged coordination, the puff of the tuba is going to occur exactly when it's opposite the station keeper. So what the station keeper sees is this. The train moves along, and the sound enclosed inside the air inside the train has also continued to move along with the train. Therefore, since the car moves, this sound here has gotten less far than this sound over here. And therefore, it's going slower relative to the station keeper than the forward sound. But the relative speed of the sound back and forth in the train is the same. The station keeper also sees the front and back passengers wake up at the same time. So now we come to special relativity. And we add to, I've added here a shorter formulation of relativity. The laws of physics are the same in what we call inertial reference frames. Inertial simply means that there are no relative accelerations, these smoothly moving points of view. And by laws of physics, Einstein didn't just mean motion. He also added to it any other rules like the electric and magnetic fields and how they act. The second thing that Einstein postulated for special relativity is he simply took as given that the speed of light will always be measured to be the same. The speed of light is a symbol c, and you only need one for it because it's always going to be the same no matter where you are, no matter how fast you are moving, and no matter how fast a light source is moving relative to you. Why would Einstein make light speed the one true constant and not time? And he bent everything that we knew to fit this. Well, that's because it was pretty well motivated in Einstein's day. There were problems in their understanding of physics with theory when it came to electromagnetism. It appeared to predict a single speed of light no matter how fast you were going relative to the source. The other thing was that observationally, people were beginning to get sensitive experiments that should be able to tell a difference in the speed of light because if the light was a wave, all waves have a speed relative to the medium that carries it. Therefore, if you're moving relative to that medium, you should see a different speed for that wave, like you see a different speed for the two waves of sound. But no one was finding any difference in speed. And this constant speed of light, by the way, has been tested to death and appears to be perfectly true. No experiment has been able to contradict it. And all of these weird results that we get from special relativity that it predicts also seem to happen. So what do I mean by weird results? Let's go back to our physicist's ideal train car, again with our two sleeping passengers. They're deaf. We aren't going to be able to wake them up with the tuba. So we brought along a flash bulb. What's going to happen is we're going to, at some time, flash the flash bulb very briefly. The light goes on, and the light travels through the train car from the center and wakes them both up at the same time. This is exactly what we would expect to see if we were sitting in the train. Now imagine when we've got a speed limit in the universe of the speed of light. This is going to be shown first from the point of view of the train. We have a station master here, and from the point of view of the train, the station master is moving to the side at half the speed of light. When the light goes on, you see a flash. And what I'm about to describe goes for anybody within the train. It's this train's point of view, this train's reference frame. Anybody in the train will be able to compare notes and realize that the same thing has happened, because this reference frame connects all of the train, all of the observers inside it. And they've all been able to synchronize their watches ahead of time. So you send off a flash of light. The station master moves to the side. And by the time that the light gets to the front and the back of the train, the station master has only gotten halfway from the center of the train to the back. Let's look at it from the station master's point of view. The train now is moving off to the side with half the speed of light by relativity. You both see the same relative speed. We're going to have a single flash of light. This has been prearranged to happen exactly when you're opposite the conductor. You can imagine the conductor is actually holding something which completes a circuit on the train. So this will happen at exactly that point in time. So now, the flash of light occurs as the train is moving. And now I'm drawing the light in the train where it is and also relative to the conductor. So you can see it's symmetrical about the station keeper here. The station keeper cannot see a different speed of light to his left than to his right. Therefore, this is how far the light gets as far as the station keeper is concerned. Of course, the train is catching up to the flash of light because it's moving at a substantial fraction of the speed of light. So the light flash has gotten further to the back of the train than to the front. This means the back guy is going to be woken up while the front guy is still snoozing, takes all the way out to here. There's a substantial difference in time between when this guy woke up and when that guy woke up, which is very different from what happens when you wake them up using sound, using Galilean relativity. Keep in mind this does not have to do with light taking a little bit of time to inform this guy over here that this guy is woken up. We're talking about things from the conductor's vantage point. We can include a series of friends standing shoulder to shoulder with him, all with synchronized watches, and the guy out over here will measure a time that is later for this guy waking up than a guy out over here would have measured for this guy waking up earlier. So this is what I'm going to call our first piece of uncommon sense. Things that happen at the same time from one point of view do not have to happen at the same time to another observer when these observers are moving. We've just shown that. It required the events to be separated in time, separated in space, and the observers to have a relative speed. This should strike you as extremely weird. I'm going to limit the weirdness slightly. This isn't a complete free-for-all about when things happen in the universe. The fact that nobody can outrun the speed of light helps keep the universe sane. By that, I mean that you will never see an effect before a cause. As a concrete example, you can imagine there's an explosion, some pretty fireworks over here, and far away, a little boy sees them and starts to draw a picture of them. Well, because they happened far away, it takes some time for the light to go from the explosion to the little boy and let him know that it happened. Well, we can imagine there's another observer involved here who's moving relative to the little boy pretty fast, Mr. Happy Face. Mr. Happy Face cannot be going faster than the light. So as far as his point of view, this entire reference frame that is carried along with him through space is concerned, there was an explosion and there was a signal sent off, and there was a little boy who was some distance away. You can see that it takes a little while for light to get from the explosion to the little boy, because this reference frame cannot outrun that signal. Therefore, even though Mr. Happy Face observer and the point of view of the little boy may disagree about how long it takes between the explosion for the information to get here and for the little boy to start drawing, they will never disagree about which one happens first. So we get to keep one piece of our own common sense, but not much. A short digression about synchronizing up these clocks. We just saw that clocks couldn't be synchronized with the train because things that happened at one time in the train, from the train's point of view, didn't happen at the same time as far as the station keeper was concerned. Take this statement. They launched the rocket in Florida exactly when Big Ben tolled noon in London. Is this statement a sensible, sensible statement? If you were to say, did this happen, would it be a sensible question? This boils down to, can you connect the clocks way over in London with the clocks way down in Florida? This could be just connecting clocks that are separated in distance, not necessarily worrying about clocks that are moving relative to each other. But it was a serious question in Einstein's day. They were still trying to measure the size of the Earth in that era, trying to measure longitude. There are international conferences about how to establish a longitude system around the globe. And he would have schemes like sending time over the telegraph from Paris to some place in South America, so they could both keep track of at what time did they see something happen in the sky, like an eclipse. And from sort of the angle of something in the sky in Paris and the angle of something in the sky in South America, you can find the angle between them, and that tells you the longitude difference. So they also had to keep track, however, of the fact that it would take some time for that time sent from Paris to get across the ocean on the telegraphs. This idea of needing light signals to connect clocks was something that was occurring in the society. It was also an issue with railways. As you can imagine, to have a proper schedule for railways, you need to have the clocks synchronized on every city along the railway line. Otherwise, no one knows when to go to the station, because they don't know what time 10 o'clock is if you said you were going to arrive in town at 10 o'clock. Which 10 o'clock? Across cities, people had synchronized clocks, because this was a sign of modernity, that your clock on the public building, your own clock that you've set relative to it, the clock on the train station, all measured the same time. Therefore, you could schedule yourself as a very modern person down to the minute and know the right time to get to your appointments. This, incidentally, was something that was so important that people had schemes for electrically connecting clocks. And they had patent applications, some of which went through the Berne Patent Office during Einstein's work there. This is just to make the point this was not just an ivory tower type speculation about the nature of time. There was some small connection between what was going on with time, how to connect clocks, and Einstein's own work in his day-to-day life. Something which, if you want to read more about, there's a book by Peter Gallison called Einstein's Clocks, Poincaré's Maps. It goes into detail. Anyhow, that's all the historical context you're going to be getting from me, because I'm not an expert there. We're going to get back to the meat of the problem. To talk about what happens to time, we need a clock. And with a constant speed of light, a very nice way to make a clock involves sending light up from some source here to bounce it off a mirror and bounce it back. If you know the distance up to the mirror and back, you know the length of this tick because you have a single speed of light, and it's very well measured. It doesn't just go for these light clocks that we're about to explore, because you could take any clock, including your watch, and synchronize it here and say, make it tick every time that this one ticks. So the effects that they show go for any clock. Now, the reason we use light clocks is it's really easy to see how time stretches with them. Watch and you'll see the red clock caught the ball of light before the blue clock did. This is because the blue clock is moving as it ticks. Since the speed of light is constant, unlike a basketball, if you're moving along, you can't speed up light with you. The path of the red tick is going to be shorter than the path here of the blue tick. Therefore, as far as red is concerned, blue's tick must last longer. So this is the uncommon sense part number 2 about time dilation. Red is sitting still. It just sees light going up and down and up and down. That's its tick. It sees the same size light clock with blue moving past it, which therefore has a longer distance for its tick of light. Therefore, blue's clock must be running slow. Its tick, its second, if you've synchronized a tick to be 1 second, is longer than red's clock. But blue, as far as it is concerned, is sitting still. Red is moving past it off this way. So blue, as far as it is concerned, is just sending light up and down, up and down. It has this original tick when it's sitting in its own reference frame, its own point of view. So blue's ticks are shorter to itself when it is sitting still than to anybody who sees it moving. And that's the essence of time dilation. So this unchanging speed of light, where you bounce the light, unlike bouncing a basketball, requires you to change the rate of time. It takes longer for the one moving to experience a second, and if you really want to bend your head a little bit, you'll realize that as far as blue is concerned, red is moving past him, and red's clock must be moving slow too. Both of these are time dilation. So we're going to put this together and make it even weirder. This here is an asteroid in the deeps of space. It's long and thin, and we're really worried about how long it is, because if it's too long, it could be big enough to be a planet killer. So somebody came up with a scheme to measure its length by sending up light clocks towards it. We've sent up 2 light clocks, a blue one and an orange one, and they're just superimposed on each other here at this moment. Their positions coincide. A while ago, they put the blue light clock at rest relative to the asteroid, and they sent the orange light clock to be moving at a certain speed past the asteroid. The blue light clock and the orange light clock, by relativity, both see the same relative speed. And they can even determine that speed by pinging light off of each other as they approach each other, as the asteroid and the orange light clock get closer and closer. They would see the pings coming at shorter and shorter times and be able to precisely measure that speed. So what happens is, orange is moving very, very fast. So one of its ticks takes a little longer than one blue tick. This keeps on going. By the time it gets 2 ticks on the orange, it's 2.5 on the blue, and so on. And I've carefully measured the asteroid to have 4 orange ticks. But notice what's happened with blue. Blue, sitting still next to this asteroid, so it's in the asteroid's frame of reference, the asteroid's point of view, sees that it takes 5 ticks for this orange light clock to pass it by. Whereas as far as the orange is concerned, they're sitting still. The asteroid is zipping by the orange clock. The asteroid only takes 4 ticks to pass, but they're the same height of the light clock. These are the same length of ticks. So you have a shorter time as far as orange is concerned for this asteroid to pass it by than as far as blue is concerned for the orange clock to pass the asteroid by. With a shorter time and the same relative speed, orange is actually seeing a shorter asteroid. This is the part of the result of special relativity called length contraction. And it's all because we have this constant speed of light. This constant speed of light required time to dilate. You can imagine, because there's a constant speed and you've futzed around with time, that you're going to futz around with space as well. That's why we get this length contraction. And stretching out time doesn't allow your clocks to stay synchronized. If they both start out here measuring 0, out over here, this one measures 5 and this one measures 4. Therefore, they can't stay synchronized. That's why we have things that happen simultaneously from one point of view and not simultaneously from another. They actually are not always measuring the same thing at what they would think would be the same time. Now, in case I haven't given you an idea how profoundly strange this is, we're going to do something completely weird. We're going to consider the fact that the effects work both ways. I told you that the orange clock, as far as it is concerned, sitting still, it sees the clock next to the asteroid that is passing it by, running slow. So the blue clock sitting still next to the asteroid sees the orange clock take 4 ticks to pass it by. The orange clock sitting still sees the asteroid passing it by takes 4 of its ticks, but that the asteroid's clock, the blue clock, from the orange's point of view, is only going to take a little more than 3 ticks. So we look at this from the point of view, the frame where the asteroid is moving towards you. This over here is what we used to call the orange clock's point of view. We have 2 of them now. They're synchronized because they have no relative speed. You can maintain a synchronization. And they're both 0 when the asteroid starts to pass them by. By the time the asteroid has passed by, it's 4 ticks on both of these guys and only 3.2 over here. And you notice that I have contracted the asteroid properly. It was longer before, as we go back out to the frame where the asteroid is sitting still and the clocks are moving by. So now the second clock is off to the side over here. And these clocks are moving very fast past the asteroid. And after 3.2 ticks, since we've squeezed the distance between these two because they're moving, this back one will have reached this side of the asteroid. So these two parts are the same again, but this one obviously hasn't gotten past over here. Now, you're going to have to trust me on the math here, but from the point of view of the asteroid, the two clocks weren't synchronized to begin with. That's how we avoid the contradiction. The asteroid clock doesn't see these two clocks synchronized. When this one measured 0, this one had to measure something else. And of course, by the time that it reaches out here, this one will measure 4, and this one measures 2.5. The math for this is really just algebra, but it's not fun to go through pages of it. If you think it's fun to go through pages of it, you're probably already an undergraduate in physics. That's how you do spend your Saturdays. And if you aren't, why aren't you? So, we've decided the universe is designed to drive physics undergraduates mad. We add a constant speed of light to the concept of relativity to keep physics the same in all reference frames. And we find that things can be simultaneous to person number 1 and not to person number 2 moving relative to 1. They are both right, and neither one of them is right, because there is no sense of absolute time in order to keep the speed of light constant. And of course, moving clocks are running slower, and moving objects are getting shorter. So we go back now to relativity with Einstein, to our two frames of reference. Remember we had these very simple ways of connecting where things were from one point of view as moving with respect to another point of view. Our problem now is that we cannot have the same time. The way that this gets solved with Einstein is by making things a little bit more complicated in what are called the Lorentz transformations. You do not need to remember this math. There will not be a quiz. What I want to point out is that you now, to change time, mix up time and space. And both time and the distance, where there's this relative motion, have this stretch factor that physicists call gamma. Gamma as a stretch factor will be only 1 when you're not moving. That means that there is none of this time dilation and length contraction. But as you can see here, this is your own speed over the speed of light. When this gets large, this part down here gets small, and this gamma factor overall gets very, very big. And that is what we would see in terms of time dilation and length contraction. It works for everything. It means that there's a different way of adding up speeds. And when that happens, you never add two speeds, say 3/4 of the speed of light over that way, and 1/2 the speed of light that way. You can take a look at that and say that the speed at which they are receding from each other is 1¼ times the speed of light. But if you were to look at that object's point of view over there and measure how fast that guy was moving away from him, from that object's point of view, that relative speed would never be larger than the speed of light. The other consequence of having to futz with these equations and making a more complicated way of adding up speeds is that when you add any speed to the speed of light, you automatically get the speed of light back. And when you use these ways of connecting positions and so on, it works not just for motion, but it also smooths out these problems with electromagnetism. Electric and magnetic fields work from all points of view at all speeds. So why isn't this obvious to us? Why do we have to get over our own common sense to understand this? It's because it simply doesn't happen at everyday speeds. It's all in this gamma factor that stretches time and space. And the difference of gamma from 1 for small speeds goes something like your speed over the speed of light squared. So if you're sprinting, if you're a good sprinter, you're probably moving at about 3/millionths of a percentage point of the speed of light. That's very, very slow. Your difference here in gamma from 1 is only going to be 1 part in 2,000 million. You're not going to notice things compressing in length as you do your daily run. Even in air travel, you're moving at roughly 1/millionth of the speed of light. That means you are going to age a little bit less than the people that you left behind at the airport. But it's only by about 1/billionth of a second per hour of flight time, so I'm afraid that the jet set is not the fountain of youth. It does get more obvious quite quickly as you get nearer to the speed of light. When you get to 1/10 of the speed of light, you're going to see about a percentage effect in this gamma factor. At a half the speed of light, you're going to see about 15% effects. Astronomy has a big advantage for seeing this. If there is some sort of effect that you can see accumulating over a large distance, hey, we've got huge distances out there. But especially, as I mentioned, there's lots of energy out there. There are things moving at very high speed, substantial fractions of the speed of light. Now, you could imagine that if the speed of light were much smaller than what it is, we might actually notice these things. But it would have to be phenomenally small for us to see the effects. If the speed of light were only 100 miles an hour, and you, in the modern age, have cars and trucks and trains moving at, say, 50 miles an hour, so half the speed of light, you might start to notice that long-distance truck drivers and people who work on trains are looking pretty good for their age. But it's still only a 15% reduction in the rate that they age during their trip. They are not going to end up with an effect where they leave town and leave their toddler behind and come back to find an adult whom they've missed their entire childhood. So that would be why we don't notice it. There are other things that do notice it. And if you were here a couple of weeks ago, you may remember the example of the muon. This was one of the first things that gave a really concrete example of these special relativity effects of time dilation and length contraction. A muon is an elementary particle, much like a heavy electron. It was discovered in the 1930s, so its behavior when it moves very quickly was predicted long before it was ever known to exist. They're typically produced when you have high energy cosmic ray particles at the top of the atmosphere. They interact with our atmosphere's particles, and these produce muons. Now, they're fragile. If you could manage to, they typically move very quickly down the atmosphere, but if you could stop some, and you can do that with certain instruments, you would notice that they are very unstable. They last only about 2 millionths of a second on average. If you had a box of muons on the table, you turn your head around, they'd be gone. Now, by about 2 millionths of a second on average, I mean it's a very typical kind of instability that's very well understood. If you start out with a certain number of muons out here, you have a certain fraction left after each lifetime. After the first 2.2 millionths of a second lifetime, you've got less than half the muons left. Out here at 3 lifetimes, less than 1 in 10. After 5 lifetimes, you've got practically no chance of finding a muon. So, you can observe that aging really does slow down. We have our muons here shown schematically as green balls. They aren't actually green balls. And 2 black box detectors that do a great job of detecting exactly how many muons there are at the top and at the bottom of this mountain. The mountain we've decided is 3,000 meters high. That means with the muons moving near the speed of light, it takes about 10 millionths of a second for the muons to get from the top down to the bottom. That's 5 muon lifetimes. You would expect that if you measured 7 muons were at the top here, there's almost no chance you would see even 1 muon surviving to the bottom. But relativity has actually slowed down the muon's clock. In this case, they do indeed find a fountain of youth, as far as we're concerned. About half of them survive to the bottom at typical muon speeds. This, of course, isn't what the muon sees. The muon doesn't see its own clock as slowing down. As far as it's concerned, it only has about 2 millionths of a second to survive from this top of the atmosphere. But lo and behold, there is a mountain coming up at him at nearly the speed of light while the muon is sitting still. That mountain, however, is not nearly as impressive. Because the length is contracted for this moving object, moving relative to the muon, that mountain is only about 430 meters tall from the muon's perspective. Well, the time for that mountain moving at near the speed of light to get from the tip of the mountain to the base of the mountain past the muon is only about a half-light of the muon. Therefore, the muons sitting still will see about half of them survive. So you get the same effect by relativity. You have to have the same result in the experiment, although there are two different parts of the explanation in special relativity. We see time dilation, but the muon sees a large length contraction, and therefore that's why it's likely to survive the trip. Now, the second interesting consequence of special relativity is this most famous of equations, E equals mc squared. I wanted to leave you with an appreciation. This is not a separate theory. It was elaborated in a separate paper, but as a consequence of the physics of special relativity. It doesn't need this addition of gravity that comes into what's called a general relativity theory, but simply can be developed by understanding what happens to objects under special relativistic conditions. There's more than one way to get at it, and the way that I want to spell out involves momentum. This is the physical quantity of motion that we see at ordinary speeds as the mass times the speed in the direction of motion. It's one of the great conserved quantities in physics, and it's how we understand collisions and so on. You can see a lot of conservation of momentum on the billiard ball table. The only way to change the total momentum that you are observing is by having a force outside of all the particles whose momentum you've been measuring. So we're going to start here by considering a wave here in the ocean. And any wave has this pattern. So this is the wave pattern of water in the ocean. It's moving off to the side here. But what is actually moving is not all the water in the ocean. You could imagine that if you had this wave pattern and all the water that forms the wave pattern is moving to the side, you'd be skimming off the surface of the ocean every time waves crashed on the shore. Pretty soon you'd have flooded the interior and completely emptied the ocean. What is actually happening is that the water is cycling up and down with a rhythm that produces the wave pattern. It's the top part of the rhythm here and the bottom part over here. So as they cycle, this crest moves along. The momentum of the water is up and down, but we all know that waves can push things. Therefore, waves have momentum. The wave pattern itself has momentum going off to the side. This also is relevant when it comes to light. We can imagine we have an atom here, an isolated happy pink atom, that has a little bit too much energy. So it lets off a photon. And we would observe that if it lets off a photon, there's a certain recoil. It starts the atom moving in order to conserve the total momentum. So light is a wave and has momentum. And it's observed that light's momentum is proportional to its energy. That is actually a general wave property, that the wave will have a momentum proportional scaling with its energy. So we're going to look at this again. We're going to call this the frame of the atom, or more accurately, the point of view where the atom starts out at rest. It has a lot of energy, and this time sends off two photons, one up and one down. Because these two photons, we decide, have the same energy, their momentum is going to cancel. Since there's no change in the total momentum, there's no kick given to the atom this time. The atom started at rest and stays at rest. It cannot change its speed. Let's look at it from another point of view, where we're going to call the lab frame, where the atom is moving at a smooth speed across our point of view. We're just going to continue this schematically with an arrow. The same thing is happening. At some point here, the atom, sitting still relative to itself, is sending a light beam up and a light beam down to get rid of energy. Now, just like when we had the cart moving here with Godzilla, that ball was tossed up but also kept on moving forward, you can imagine that the light beams are also tossed forward like this. Well, now their directions are no longer straight up and straight down. So part of the momentum is going to cancel, but not the momentum forward. The photons have some forward momentum, but this total momentum of the atom, which was already moving forward, can't change. That means we have to take out some of the atom's forward momentum to get the same amount of forward momentum that we used to have. So to make something cancel, we don't change the atom's speed. The only thing that's left with momentum is the atom's mass. The photon's momentum is proportional to the photon's energy. And therefore, the mass lost has to scale with the energy of these photons. Exactly so that the mass m lost is E over c squared. Or we've gotten this exchange where we get this energy E out of mc squared. So why is this important to me as an astronomer? Well, it's for the same reason that I chose a star field here as a backdrop for the talk. The stars are quite connected to special relativity, and particularly to E equals mc squared. E equals mc squared is at the heart of the nuclear reactions that make stars shine. You turn hydrogen into helium, and if you were to weigh everything before and after, you would find the helium weighs less than the original particles that go into making it. This difference in mass is converted to energy, which is released as light. This goes for all the stars that we see in the sky. And the other part that relates very directly to special relativity is that when we look out at the stars in the sky, we're not seeing them as they are right now. Since the universe has a speed limit, it takes time for the light to come to us. We see as the stars long ago. And for each star with a different distance relative to us, we're seeing it at a different point in time backwards. And this goes, of course, not just for our own neighborhood, but for things much further away, such as other galaxies. And we've now come to the end of our overview of the anti-commonsensical common sense of special relativity. Next week, I'm going to go beyond these fairly basic results about why we see time stretching and lengths contracting. We're going to get further afield into astronomy, where we're going to see the games that relativity plays with the light that we receive. We're going to see how it affects the colors of objects and some truly bizarre results that we see in jets that are accelerated to nearly light speed. Thank you.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program. Local broadcast is made possible in part by Pfizer.